The topic of this lecture will be the acid-catalyzed opening of epoxides. Despite the high ring strain of an epoxide, they are actually surprisingly stable molecules. However, they are not stable in acidic solutions. If we dissolve an epoxide in an aqueous acidic environment, it will open up to give a diol. Because the addition of water to the epoxide has an SN2-like mechanism, the new hydroxyl group adds anti, and we end up with hydroxyl groups on opposite sides of the molecule. Additionally, this works in a Markovnikov fashion. The water attacks the more substituted carbon, although we won't be able to see this in the product until we look at the next reaction with an alcohol instead of water as the nucleophile. In order to understand the stereospecificity and regiospecificity of the product, we need to look at the mechanism. In the first step of the mechanism, the epoxide oxygen is protonated. This produces the protonated epoxide, which is a very good electrophile because of the positive charge and the ring strain. In the next step, water attacks the epoxide by directly forming a bond to one of the carbons of the epoxide. This happens in an SN2-like fashion, meaning that the water has to attack opposite the leaving group, which is the epoxide, causing inversion of the stereochemistry at that stereocenter. In the final step, another molecule of water deprotonates the diol to produce the product. This acid-catalyzed opening of epoxides can be used in conjunction with epoxide formation to turn an alkene into a trans-diol, like this example. If we treat this alkene with a peracid in water, we will get the epoxide that is quickly opened to give the diol. Remember that the byproduct of the peracid is a carboxylic acid, which helps to acidify the solution and allow the water to add to produce the trans-diol. If we would prefer instead to produce just the epoxide, we can use peroxy acid in a non-nucleophilic solvent like carbon tetrachloride. For example, if we treat the same alkene with MCPBA and in carbon tetrachloride, we will produce the epoxide in nearly 100% yield. Finally, water is not the only nucleophile that can add to a protonated epoxide. We can also add alcohols. If we treat this alkene with a peroxy acid and an alcohol, such as methanol, we will produce the epoxide, but the epoxide will very rapidly be opened up to form an ether alcohol functional group, a pair of enantiomers. However, if we treat this alkene with a peroxy acid in methanol, we will get an epoxide as a pair of enantiomers that will be opened up to give, again, the ether alcohol functionality. However, we will get only these two enantiomers because of the regioselectivity of this reaction. The methanol adds to the epoxide in Markovnikov fashion.